camera lens is an optical lens used in conjunction with the camera body. It is a mechanism which is used to store an image on a photographic film or any other material chemically or electronically. The classic definition of a lens is that it is an optical system consisting of at least two refracting surfaces, out of which one is curved and the other can be any non-linear surface like parabolic or elliptical. In terms of photography, the understanding of a lens is quite clear. That is to say, we have a normal lens, that is a lens which gives a normal view to the human eye. We also have a wide angle lens which gives a wider view to the subject. And third, we have a telephoto lens which gives a closer view of the subject. Besides this, we also have macro lenses, we have fisheye lenses and even PC lenses. To elaborate further, a normal lens is the one the focal length of which is equivalent to the diagonal of the negative that it produces. On the other hand, a wide angle lens is the one whose focal length is less than that of the normal lens, and quite to the other side, a telephoto lens is one whose focal length is more than that of a normal lens. Let us now see lens properties in relation to photography. We have the aperture, for example. The aperture is the iris or the opening of the lens, which is marked in terms of f1, f2.8, f4.5, f5.6 and so on. This aperture works out the amount of light that has to go through the lens onto the film or the recording material. Aperture, when it varies, the amount of light also goes on varying. The second point to note is that it has a depth of field. That is to say, depth of field is the area within which a picture is within the acceptable sharpness. Even if we may focus on a particular object very sharply, we will find that some area in front of it, which is 1/3 and 2/3 behind, is generally in acceptable sharpness. The third factor is that with the lens we can focus sharply on any object. We also have a distance scale, that is to say, we can measure the distance between the camera and the object. Every lens has a field of view. That is to say, if you look through the viewfinder, we see a particular area which is visible through the lens. In the case of a normal lens, we get a normal field of view. In the case of a wide angle lens, we get a wider field of view. And in the case of a telephoto lens, we get a we can home on to a particular subject. That is to say, we can go closer to it, we can isolate it. Similarly, we have a zoom lens, in which case we can vary the field of view depending upon the composition and our requirement of the final picture. We know that there are basically two kinds of lenses, the concave lens and the convex lens, which are shown in the diagram. Besides this, we can also have a plano-convex lens, we can have a plano-concave lens, we can have a concave convex lens, we can have a convex concave lens, and there are permutations and combinations. Let us now see image formation. As I mentioned earlier, we have a convex lens and we have a concave lens. Let us see how each one of them behaves. In the case of a convex lens, we have an image forming across the lens or beyond the lens, which is a real image which can be recorded, as shown in the diagram. On the other hand, concave lens forms a virtual image in front of the lens, as shown in the diagram. Let us see another aspect which is very important, and it is known as image magnification. It is the ratio of the size of an object with relation to the image. Let us say if the distance between the lens and the object is u, and the distance between the lens and the image formed is V, then we have the magnification which is V upon U. Now, if V is longer, U is smaller, we will get a magnification of a higher size. On the other hand, if the U is larger and the V is shorter, then we will get an image of a smaller size. This is applied in terms of photography, that is to say, when the subject and the lens distance is smaller, that is U is smaller and V is larger, we get a telephoto, we get enlargement, we get a bigger image. On the other hand, when U is larger and V is shorter, we get a wide angle image of the subject. That is to say, if the lens moves closer to the object, the image becomes larger and vice versa. Let us see another aspect of lenses which is known as lens defects. The following aberrations or the aberrations which follow directly lower the sharpness of an image, and they are chromatic aberration, spherical aberration, coma and astigmatism. We will see them one by one. Chrome means color. Colors have different wavelength and behave differently. Violet, which has the shortest wavelength, moves closer to the lens while the others move away from the lens accordingly. Similarly, chromatic aberration is a type of distortion in which there is a failure of the lens to focus all the colors of the spectrum at the same converging point. It occurs because lenses have a different refractive index for different wavelength of light. The refractive index decreases when they increase in wavelength. Chromatic aberration is noticed on the fringes of color along boundaries that separate dark and the bright parts of the image. Because each color in the optical spectrum cannot be focused on the same point, chromatic aberration can be corrected by using a combination of a convex lens and a concave lens, because concave lens behave quite the opposite of the convex lens and therefore they neutralize the effect. This is known as achromatism or minimization of chromatic aberration. Alternately, chromatic aberration can be controlled by monochromatic light, which means light of a single color. However, in terms of photography, this is rarely used. Let us see spherical aberration. We know that a lens is part of a circular ball which can be a perfect circle or a parabola or even elliptical. That is to say that the radius of curvature of the lens is higher at the center and lower on the periphery. It is an optical problem that happens when all the incoming rays end up focusing at different parts after passing through the spherical surface and end up in different parts or different spots across the lens axis. In other words, the parallel rays of incoming light do not converge at the same point. Because of this, spherical aberration can affect resolution and clarity, thereby making it hard to get a sharp image. Spherical aberration is not just caused by the lens design, but also by the quality of material which is used in making this lens. Lenses made up of poor quality material and large bubbles can impact the light refraction. A perfect lens will have all the rays converge onto a single point, as illustrated in the diagram. Spherical aberration is most pronounced when the diaphragm of the lens is wide open, that is fully open. It can be reduced by stopping down the lens. Stopping down the lens even by a single stop can dramatically reduce spherical aberration. removal of spherical aberration is possible by using a plano-convex lens or by stopping down the lens, or by using blocks on the periphery of the lens, or by using a combination of convex and concave lens in contact, or by using two plano-convex lenses of the same material at a suitable distance. Let us see yet another lens defect, and that is coma. Coma is an aberration in which light rays pass through off-axis point, causing the lens to focus at different points, resulting in a blur. It is a lens aberration producing a symmetrical distortion of points in an image. In coma, the image of a point source of light is prevented from being brought into focus. It is a lens defect which results in points of light appearing in the image not as points but as discs with comet-like tails. This refers to blurring of the objects at the edge of field of view. The term has been taken from the shape of the image, which is like a comet. Coma can be reduced by stopping down the lens. We will now take another defect which is known as astigmatism. This defect arises due to development of different curvatures along different planes of the lens. This lens aberration makes a single point lighting source impossible to focus as a true point. It is imaged instead as either of the two short lines at right angles at different distances from the lens. This is a real problem because light rays passing through the lens in different planes get focused at different points. This occurs when the subject is much off the axis or when inclination of light is much higher. To remove this, we block the rays coming from higher inclination and are cut off, or we have an appropriate combination of convex and concave lens. Flare is yet another defect which occurs due to the various elements forming a lens. Now, each element of a lens reflects certain amount of light back, and some of it may go to the film, thereby causing a ghost image. Flare is much reduced when the glass air surfaces within the lens are coated with metallic fluorides and the interior of the lens is coated matte black. Flare has greatest effect on image shadows, which it degrades, thereby lowering contrast. We now know that flare is caused by a partial reflection of light from the lens. Mirror has 100% reflection, while a lens does not have 100% reflection. In the case of lens, there is partial reflection and partial refraction. Let us take the case of a rear view mirror in the car. What we see is our own reflection, which is 100%, while that of the interior of the car is basically refraction. We can conclude this topic by saying that lens defect occurs due to various reasons. Primarily, they affect sharpness of the image. They can be spherical aberration, chromatic aberration, coma, or astigmatism. Flare is also one of the defects that can be included in this. Through various permutations and combinations, it is possible to minimize these defects and thereby get an image which is acceptably sharp.